Most people fail to learn Rust because they try to understand the hardest Rust concepts in isolation. But in real production Rust, these concepts show up all at once. These few lines of Rust code are proof. This is essentially how Tokio's sleep works under the hood. And packed inside this tiny example are macros, async functions, lifetime parameters, and unsafe Rust, all colliding together. So in today's video, we'll deconstruct this code snippet so you can internalize the 4 hardest Rust concepts in only 10 minutes. So grab a notepad, get your popcorn, and let's dive right in. This video is presented by the Rust Live Accelerator, and today we're officially opening applications. More on that later. First, let's set the stage and just understand high level what this code is doing. Our sleep future is doing one simple thing. It periodically checks the clock. If it's too early for the set duration, it comes back and checks again later. And once enough time has passed, it returns done. Now, let's go back to the syntax and unpack how this is happening inside our code. The first thing you'll notice is this attribute on top. Tokio main is a macro, the first of the 4 hardest concepts in this file. A macro is code that writes code. Its whole purpose is to kill boilerplate. Instead of handwriting the same setup every single time, you can capture it once and reuse it with a single line. And here's the key thing about macros. They are hard to write, but easy to use. Writing one means writing a program that generates correct Rust code for every possible input, which is genuinely difficult. But using one, like we are here, is simple. Let's unpack what this single line does for us. This is what the Tokio main macro expands your code into. It builds a multi-threaded runtime, and then runs your async function on top of it. You wrote 3 lines and the macro generated 10. Now let's head back to our original code. Right below the main macro is async function main and sleep new, which are both async functions. Async Rust is the second of our 4 concepts. Every async function in Rust returns a type that implements the future trait. A trait is Rust's word for an interface. To implement the future trait, you need 2 things. First, an output type, what the future hands back when it finishes. Our sleep returns unit. Unit is simply Rust's way of saying a function returns nothing meaningful. Here, we only care that time has passed. And second, a poll method. This is the method the async runtime calls over and over to ask the future, are you done yet? Now, poll takes a couple of arguments, but the one that matters here is context. And the context is where our third concept appears, lifetimes. See this tick underscore? That is a lifetime annotation. Now, what does this mean visually? Lifetimes exist in Rust because Rust guarantees memory safety without a garbage collector. But to do that, the Rust compiler has to be certain that no reference is ever used after the thing it points to is deallocated. Now, here's why the tick underscore syntax shows up. The context struct has a mutable reference inside of it, and anything carrying a reference inside has to declare how long that reference is valid for. That's what a lifetime is. A label for the window where the reference is safe to use. The tick underscore syntax here is an anonymous lifetime, which means we want the compiler to infer the scope where the reference is valid. The scope of the lifetime starts right here at the first curly brace, the moment poll is called and the runtime hands the context in. And it ends right here at the last curly brace, the moment poll returns. After that, the reference becomes invalid, and the compiler will reject any code that tries to use it. So that is all a lifetime really is. The compiler's guardrail. It marks the scope where a reference is valid, from beginning till end, so mistakes get caught before your program ever runs. Now let's fill in the body of our poll method. The very first line of the body is this unsafe block. The 4th concept, unsafe Rust. Rust actually gives you 2 modes. Safe Rust is the default. Every reference and every memory access gets checked by the compiler, and anything it can't prove is sound gets rejected. Unsafe Rust is a way to opt out of Rust's strict safety checks. It lets you run a small set of operations the compiler can't verify on its own. That does not mean the code is bad. It means the compiler can't prove it's correct. So you're telling it, I have checked this myself. The catch is, you have to be right. If you're wrong, your program can crash. And Rust needs this escape hatch, because some things genuinely cannot be checked by the compiler, like talking to the operating system, or to code written in other languages. Here's the mental model. Everything the compiler can check for you is safe Rust. The moment you step past what it can see, the operating system, raw memory, or a foreign library, you cross into unsafe, and the checking becomes your job. The unsafe keyword is just how you mark that crossing. So why is our line unsafe specifically? It comes down to how self is passed in. Self is wrapped in something called a pin. Pin is a promise from the compiler that this value won't move in memory. Why does pin matter here? Async futures can end up holding references to data stored inside themselves. If the future were moved in memory, those references would still point to the old location, making them invalid. Pin is what guarantees the future stays in the same place, so those references remain valid. Think of pin like a lockbox. The compiler has sealed your value inside it and is promising the value won't move in memory. If the value moved, those references would be left pointing at the wrong place. To actually reach in and mutate the value, you have to pry the lockbox open with the getUncheckedMutate method inside of an unsafe block. The compiler can't verify you'll keep the promise that you won't move the pinned memory, so it forces you to wrap this operation in an unsafe block. And this is the common pattern you'll see in Rust. One small, carefully checked line of unsafe, wrapped inside an interface that is completely safe to use. You write the hard part once, and everything built on top of it stays safe. And now let's put everything together. We started with this single macro. Macros are often used in substantial libraries like the Tokio async runtime. The Tokio macro hides boilerplate like this and complexity from its users. Async Rust code implements the future trait, which includes the poll method and the context struct. And lifetimes are common in async Rust because async code often uses context, which contains references to the async runtime primitives. And references in Rust need to be valid, which is why we need lifetime annotations to inform the compiler how long a lifetime is valid for. In addition, unsafe shows up in async libraries because we may need to perform operations the compiler can't verify on its own. For example, futures have a poll method that needs a pinned self argument to prevent futures from moving in memory. But we also need to mutate the future while it is pinned. The compiler can't verify on its own that we're updating the future without violating pin's guarantee that the value won't move in memory. So we need to perform this operation inside an unsafe block and verify the code ourselves. You've now seen the 4 hardest Rust concepts working together to achieve a common goal inside a single piece of production Rust code. And learning to use these features in harmony is the key to writing production-grade Rust code and landing high-paying Rust jobs. This is exactly what our students are doing in our Rust Live Accelerator mentorship program. Today we're officially opening applications for the program, and the applications will stay open for just a week. There are only 30 spots available, so click the link below to apply. Inside the Rust Live Accelerator, we work directly with developers like you who want to master Rust at a professional level, use Rust at their current workplace, or land their very first Rust job. So if you want hands-on guidance, production experience, and to kickstart your Rust career, click the link below to apply. People who joined the waitlist from previous videos already got a 24-hour head start, so make sure to apply soon to reserve your spot too. Click the link and whether you join or not, you'll get our 3-step Rust developer roadmap regardless as a small gift. So tap the link below to apply, and I'll talk to you very soon.